Hey everyone, welcome to the stream. Today we are going to continue building Nand2Tetris computer, and in this stream we are going to build the final pieces of the computer, which will have a memory and a CPU. So we'll get started with implementing memory. So let's check out the slides. So as you can see, this is our final computer, and we'll create this memory and CPU pieces. Entire RAM address space. So we already have RAMs built. So we'll be just using those RAM to build this entire memory space. Instruction data. This is CPU implementation. We are not going to build it right now. We will build it afterwards. I'm trying to find the implementation of RAM. Not exactly the implementation, but just the architecture and the diagram. Memory, yes. So this is what we have to build. We have to build a chip which will have 16-bit inputs and 16-bit 15-bit address space. Oh, it is just 15-bit. Okay. And 16 bits as the output. Now this address space, and inside this memory we will have three components, which will be a RAM which we built earlier, 16K RAM. Then another chip will be a screen chip. So we have not built this chip, but it is basically a memory chip, and the Coursera instructor have provided it, so we don't need to build it. And there will be another chip called keyboard. So before we talk further, let me open up the HDL file of this memory chip. Projects will be inside fifth folder. CPU. Okay, it seems we have a lot of files in this folder, but we are just concerned with this file memory.hdl. So let me open it up. Memory.hdl. And so we have 16-bit input and 15-bit address space, one load bit as well, and 16-bit output. Alright, so let's see. We will need a RAM, a screen, and a keyboard. So let me get the 16. Let me check the names of these chips. It will be inside the built-in chips. So we want this one. Is it RAM 16? We will be needed this chip, RAM 16, and this one screen and keyboard. What is it? Keyboard, yes, this one. So let me first check the implementation of RAM 16. RAM 16. So this RAM 16 has in 16-bit input load and a 14-bit address space and 16-bit output. Alright, so this input will be the same as this one, so we will provide this directly to this RAM, and this load bit is same as this load bit, and we also have, but in this case we have 14-bit address, whereas in this diagram we have 15-bit address space. So we will have to see which bits we will be passing to this RAM. So we will have to get rid of one bit either from the front or on the back, right? And this output will be the same as this one. So let's see, now we have to select this RAM. So it will be something like this. We will have to toggle this load bit, because let me check. To check this folder, tools, built-in chips. Let's check the implementation of screen HDL as well. So this screen HDL will also have 16-bit input and a load bit, an address input of 13 bits and output of 16 bits. So this input and outputs are similar to this RAM chip. Let's see. So they are similar. The only difference is, in this case, in RAM we have 14-bit address space, and in screen we have 13-bit address space. Alright, so the idea is, based on this address space, if it lies between 0 to 16,383, we will toggle the load bit of RAM. So load bit of RAM will be 1. This RAM load bit will be 1, and load bit of screen, and I'm sure keyboard has same kind of inputs and outputs, just that the input will be similar, which will be of 16-bit load. It will also contain a load bit, and for the address, I think there won't be an address because we just have a single register. So we'll check it out later, and it will be similar for the output. We will have 16-bit output. So I was saying that based on this address, if it lies between this range, then we will toggle the RAM 16K load bit to 1, and all other load bits of screen and keyboard will be 0. Now if the address lies between this range, then we will toggle the load bit of screen to 1, and the load bit of RAM 16K and keyboard will be 0, and so on for the last keyboard bit. And what this will do is, if the load bit of any of this, so these three are just RAM chips basically. So screen and keyboards are basically the RAM chips only. So if this load bit is 1 for either of these chips, then whatever we pass as input will be stored inside the particular address which will be providing in the address, and this input will be stored at that address inside the particular chip, which will have load bit as 1, and it will also provide the output. Okay, this output, what will this output contain? Read and write. Okay, also the same output, we will have the same output as the input because we are selecting that particular address. This output bit output will always reflect whatever is inside this particular address, and we will have to provide a logic so that we can select the appropriate address from this particular RAMs. We will have to see if address lies between this lies in this range or this single address. So let's first get this three chips. Let's first get RAM 16K. Now for the input, we'll directly provide this input and load bit. We will see how to input the load bit later. So let's just keep it as it is. We'll keep it blank for now. It will also contain address. Now in this case, we can't directly provide this address to this address, so we will have to see how to provide the particular specific address. Now this is a 15-bit address, and let me open up text editor. So we have a 16-bit address. Let's see what we want to do. 16-bit address. And the address space of this RAM is of 14 bits. And we have to provide some kind of logic which will pass the specific address to this RAM. So we have to check if this address, 16-bit address, lies in this range 0 to 16,383. So how do we check it? Mhm. So out of the 16 bits, if I remove the last bit, which will be at the 15th index, so this indexes will run from 0 to 15. So if I ignore the 15 bit, or let's just say if it is the 0, then let me see the mapping between the bits. And so I want to check binary to decimal. So let's see if we have 16 ones, or not 16, 15 ones. 1, 1, 1. These are 8 ones. 8, 2, 16, 15 ones. So let's see the decimal value. It will be 32,767. Why is it that much? 2, 4, 5, 7, 6. Decimal to binary. 2, 4, 5, 7, 6. So this will be the value of this address, 16-bit address, or 24576. Now let's check it out for 16,383. 16,383. If this is the address, I mean, if the address is between all zeros and this one, then we will have to toggle the load bit of the RAM. So how are we going to do that? What chips are we going to use over here? So I guess we will use a multiplexer. This multiplexer will have, let's see what it will have. No, we will use a Demux, and the input will be the load bit. The input will be this load bit will be the input to the multiplexer. Let me try to draw the diagram. So we will have something like this. The load bit, let's just call it as L, will be provided to a multiplexer, and this multiplexer will have three outputs. First of all, do we have such a multiplexer? So we want a three-way Demux. I don't think we have such a mux. I'll have to check it out. We have this built-in chips, Demux 8-way Demux. Yeah, these are all the chips we have. We have our Demux 4-way, Demux 8-way, and a simple Demux. But we want a 3-way Demux. So let's see how are we going to select this Demux. Let's check the implementation of Demux 4-way. Demux 4-way HDL. So Demux, in Demux 4-way, we have a single input of 1 bit, and 4 outputs, and a 2-bit selector, control bit, or whatever you want to do. So if it is 0 0, it will select the first output, and so on. But in our case, we only need 3 inputs. So if we need just 3 inputs, we will ignore the 4th one, I guess. And we will have to map between this selector bits and this particular chips, either RAM, screen, or keyboard. And this particular so how are we going to select this particular bits? It will be based on the address. Now therefore we will have to see this address. We will need to build some kind of logic. We will check if this address lies between this range or this range, or this symbol. So how do we check if the address is between this or this? I'm thinking which kind of chip are we going to use over here. Hmm. 0 to 16,383. 16,383 will have this kind of binary. 16,384 will have this kind of binary value. Wait, this bit will be 1 if it is 16,384, right? Let me go back to 16,383 again. Cool. So for 16,383, this bit is 0, and for 16,384, this bit will be 1. So we can use that particular logic to select between these different selector bits. So if this bit is 0, and this will be 0 for 0 to this bit will be 0 for, I hope so, it will be 0 for, let's see, it will be 0 for any number between 0 to 16,383. So if that bit is 0, that means we know that the number lies between this range. Good. And if it is 1, then we know, wait, but this bit can be 0 for this range also, right? This bit can be 0 for number between this range as well. Okay, so we can so this bit can be 0 for numbers between this range, but it will be either this bit will be 0. If this bit is 0, this bit will either will be 1. So both can't be 0 for any number between this range, because if those both bits are 0, then the number will be between this range. So we will have to provide a logic which will check this both bits. So let me check out my theory. 16,384 for this number, this bit will be 1, but this bit will be 0. Or let's say 5, of course this bit 2 4 5 7 5 7 5 2 4 5 7 5 2 4 5 7 5. Again this bit is 1, but this bit is 0. Or 5 7 6. Let me check it for 570. Let me copy this and change this bit to 1. We have 57,000, and this bit to 0. Let's say What if all of this are 0? If this bit is 1 and all of this bits are 0, that means the number is 32,768, and this number is out of this range. So we don't need to worry about this particular bit being 1, because it won't be for any of the address, right? So we have to worry about this bit only. So, and how do we check if it is 24576? Mm, 24576. This will be the binary value of 24576. So how do we check if this address, the address we are providing is exactly this one, 24576? I mean, I know there is a one way. The one way is to just check if this 2 bits are 1 and all of the other bits are 0. That will give us 24576. But I'm thinking of another way by which we can see if this bit, this is the address space, is this number. And we can't use the ALU chip, so that's out. Alright, then I'm just gonna use the simple solution. We will check if both these bits are 0, 1, and all of the other bits are 0. And 24575. Wait, so I know. If both of these bits, if this bit is 0, that means we know that the number lies between 0 to 16,383. And if that bit is 1 and this bit is 0, the one before that, then we know the number lies between this range. And if both of these bits are 1, that means the number is either this one or greater than 2456. So in this case, we are assuming that we are providing the correct address each time to this memory. It won't be outside of this range, 0 to 2000, 24576. So in that case, we can just use these 2 bits for our logic. Now we can directly provide this 2 bits to selector. Let's see what if we do that. If we provide this 2 bits to selector, if it is 0 0, that means we know it is the first case, or even for 0 1. So check for 0 1. 1. Let's toggle all of these bits. 0 0 0 1 8192. So yeah, it lies between 0 to this range. So if those 2 bits are either 0 0 or 0 1, that means we know the number is between this range. And if it is 1 0, then we know the number is between this range, right? Let's check it out. If it is 1 and 0, 16384, which is this particular address, and we can toggle any of these bits. It will still remain in this range. But now if we toggle this bit to 1, then the decimal value will be 24576. It will be this one. So for 1 1, both bits both bits will be 1, we will select the final. So let's see what we can do. For this 2 bits, we will have this A and B will go to RAM load bit, and for 1 0 bits, the load bit will go to screen, and for 1 1 it will go to the keyboard. So let's try to implement that functionality. Let's see what we need to do. First we need to get a Demux. It will be a 4-way Demux. So let's check out the name. Demux 4-way. 4-way. And it will have a single input, right? A 1-bit input and 1 bit 4 outputs and a 2-bit selector bit. So 1-bit input will be the load bit, and see, A is equal to, we will pass this to a particular variable. Let's say it is RL for RAM load, and B will go to the same variable RL. I hope we can use the same variable for the output. And C will be for SL for screen load, and D will be for KL, key load. And we have to provide selector bits, and we can provide selector bit 0 2. We can provide address bit number, let's see, this is a 16-bit address, and we have to provide this. Let's see, Either this will be selected bit 0 or this one will be. Let me check. 0 0 0 1 1 0 1 1. So the first one will be this, and this one is address bit number. This is 15th, so 14th will be selected bit 0. I'm not sure if this is selected bit 0 or if this is, let's say if this bit is 0, then we can provide this address value. So we will see later. Right now let's pass 14 bit as selected bit 0 and address bit 13th will be selected bit 1. So I guess that is it for Demux. Now before we implement anything, let's check it out if we are getting correct outputs to this particular bits or not. So for that, let me load it inside, where is it, hardware simulator. You need to load, let me go inside with folder and memory.htl. It is saying that an internal pin may be fed once by a Firefox. Okay, an internal pin may only be fed once by a parts output pin. So I think it is giving us error for this two output bits. It's saying we can't use the same variable. So we'll just use RL1 over here. That will be all right. Now let's try to reload it again. Awesome, it is not giving us error anymore. So let me try to select decimal. So if I keep load bit as 1, and for address space, let's see, if we select a value 15,000, which will lie between this range, and evaluate it, is it not giving us the evaluate option? Maybe because we have not fed it the whole implementation. Now how am I going to debug this if I can't even evaluate it? Does this mean that I have to implement the whole chip first? Well, alright, we'll see it later then. So let me first get both of this input to a single variable. So for that I will have to Let's see what we can use. So what I want is if either of this bit is 1, then I want to toggle the load bit of RAM. So I can use OR gate, I guess. So if I pass RL as the first input and RL1 as the second input, if either of this bit is 1, I want RL2, the output in RL2. So this RL2 bit will contain 1 for whenever either of this RL and RL1 is 1. So this will take care of this load bit of RAM. Right. So let's see now what we need to do. I can pass this RL2 over here, RL2. Now we also need to map this address to either of these 3 chips. So how are we going to do that? Well, we know that this 14th bit will be 0 for all this value. So we can provide, let's say these are in total 16 bits, right? 16 bits. Oh great, we are not providing a 16-bit value, so we won't be having this final bit anyway. So we'll provide this first 14 bits directly to this RAM 16. Now do I have to provide it individually? Let me check the different slides. I'm just trying to see if I can provide a range to this input address. Couldn't preview, why? Okay, so we can provide a range. So we can do something like this. Okay, they're saying that buses are indexed right to left, from right to left. So if it is a 16-bit bus, then 40 is the rightmost. and 415 is the left, rightmost is 401. Awesome. So in this case we need to get rid of the 0th bit and only provide 1 to 15 14 indexes. 1 to 14 will be provided to this address. Now I can select a range like this, but can I select it for the output? So let's see, for address, it will be the whole address. Address is equal to address. Can I do something like this? 1 up to the 13th bit. Wait, it will be 14th bit. I hope I can do something like that. Also, we can check this bits as well. So they are saying that buses are indexed from right to left, and this will be the 0th and this will be the 1th. So in case of this addresses, 14th will be the leftmost, right? 14 will be in the left and 13 will be on the right. 13, 14. This should be 0th bit. 13 should be 0th. Yeah, so I should swap this bits. 0th bit should be 13. Oops. And 1th bit will be 14. So let's see, now it is correct. 13, 14. If this is for selected bit 0, 14 will be for the selected bit 1. Awesome. Now for RAM 16, what else do we need to provide? RAM 16 will have input, load, address and output. So we have already provided the input, a load, bit and address. Now we only need to provide the output. The output will be same as output. So now we have RAM 16 key. We need to get the screen chip, and in the screen chip will have, let me open it up. Yes, screen, oops, screen chip will have input of 16 bit, one load bit, address bit of 13 bits and output bit. So in this case as well, we'll provide the input directly. Now this load bit will be SL, and for the addresses, this address is of 13 bits. That means we will need to provide, let's see, we have 15 bits and we can only provide 13 bits. Now which 13 bits we will be providing? Now this is an issue because in case of RAM we can directly provide the address, but for this we need to do because this addresses of this particular addresses will range from 0 to whatever is the last number of 13 bit. So for 13 bit, let's see. So if we have 13 1 1 1 1 1 1 1 5 ones 1 1 these are 10 ones, right? 1 2 3 4 5 6 7 8 9 10 11. So we have 11 12 and 13 1. So 8191 will be. So this address space will be on the range of 0 to 8191. And now we need to convert this addresses to this. So what we need to do is, if this 15-bit address is 16384, then we should provide here 0. Let me try to write down the mapping. So what I want to convey basically is, for screen screen will have addresses. Let's first say for our whole memory chip, we will have addresses ranging from 16384 up to 24575. Now if it is 16384, we will provide 0 to the screen chip, and if it is 16385, we will provide 1, and so on up to this point where we will provide, let's see what we will provide. In this case we will provide 8191, 0 to 8191. Now we need to find out a way to map this input to this. Now, how will we going to do that? So let's check the binary representation of 16384. 16384. So this is the binary representation. Oh wait, awesome. So these are in total 16 bits, but in our case we will just have 15 bits. So this is all we have inside the address space. Now if we get rid of this bit, these are in total 14 bits, and if we get rid of this bit and directly provide this range, this bits to the screen, it will be 000. Awesome. So let me try to check it out for 16385. So in that case we'll have 1. So yeah, we can directly provide this first 13 bits to the screen chip. This is nice. It means we don't have to worry about any kind of logic. So we can do something like this. Now this is 0 1 and 2. We pass 2 up to 14. So I hope these are just 0. This will be 0 1. These are in total 15 bits. Wait, the address of RAM is of 14 bits. So it will start from 0 to 13. These are 16 bits. 15 bits. I think I might have a confusion. These are 13 ones, 13, 14. So 14 ones, 16, 3, 8, 3, 16, 3, 8, 3. Yeah, I think it is correct. 16, 3, 8, 3, 0, 1. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these are the 14 bits. This will be the first bit and this will be the 14th bit in our case. Now we can provide 1 to 14. This will be, let's see if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, this is correct. And in this case, we will provide, let's see, if all of these are 0, let's say 14, 15 zeros, 14 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 zeros. 16, 3, 8, 4. Awesome. So we can provide 2 to 14 to address. And also need to, the output will be, we will go into output. This is it for screen, and we need to get keyboard chip as well. Let's check the implementation of keyboard. Keyboard HDL. Okay, so keyboard chip just has one output. All right, so this means, wait, I think we might have a logical flaw in our implementation. We can't provide all of these outputs directly to this output variable. We have to keep it inside an intermediate variable, and just like we did it for this load bit, we will have to implement the same logic to select this output bits. So for that, let's see. First of all, let me write down the implementation of keyboard. It will just have a output, and we will keep it inside a let's see, KO, keyboard out. That is it for keyboard, and we'll keep the output of screen inside SO for screen output, and RO for RAM output. Now we can copy this Demux implementation, and for the input we will provide, wait, now in this case we can't use a Demux, we have to use a multiplexer because we have now 3 inputs. So we'll be using, let's see which muxes we have inside we need a mux. Where is it? So we have 16-bit mux, mux 4-way 16-bit, mux 4-way 16-bit, mux 8-way, mux 8-way, and a simple mux. Now we just need a 3-way mux, but we don't have a 3-way mux, but we have a 4-way mux, but this mux is of 16-bit. Yeah, and that's what we need. we need because our output will be of 16 bits, so we can use a 6 mux for a 16-bit. Let me open up the implementation of mux 4-way 16-bit. So we have four inputs of 16 bits, one selector bit of 2 bits, and output. So we can do, let me remove this mux. This should be mux 4-way 16-bit. We won't be having this. We will have, let's see, we have a 16-bit A. It will pass arrow to A. Similar, wait, but we can't pass both of this, so again we have to use a 16-bit OR, and A will be RO. Wait, so what I need to do over here is this, both of this input should be RO, but I can't provide both inputs the same variable RO. So what I need to do is I want to merge this into a single. I can't do a 16-bit OR because it will do a bitwise OR. What I need to do is want to have a single 16-bit variable. No, I need two variables which will have the same value as arrow. Okay, I get it. Well, in that case I can use a 16-bit AND. So AND 16-bit, and I can provide arrow as the first input. Second input I can keep it as true. Output will go into RO1. I need two of this. RO true, RO2. Awesome. Now I can provide this R1 over here, RO2 over here, and this will be SO. And D will have KO. Selected bits will remain same. Now in this case we also have output, so now this output will go into the output variable. Awesome. So now we have a way to select the addresses. This keyboard output will always contain the value that is pressed by the, so we don't need to worry about this that much. So I guess we have a correct implementation. Let's try to load it now and see if it works or not. hardware simulator. We need to load the memory chip. Oops, it is giving us an error for address 124 has an invalid subbus specification. What is it trying to say? Does it mean that we can't provide this kind of input? Has an invalid subbus specification. What does it mean? Okay, subbus, that means this range. So in that we can, where was that? We can provide this kind of range for the inputs, but not for the outputs. I have kept it like that. Overlaps of subbuses are allowed in output buses of parts. What does that mean? Overlaps of subbuses are allowed in output buses of parts. Okay. I don't get it. They are saying that it can be decomposed into subbuses, but the hardware simulator is giving an error for this kind of implementation. Maybe I have provided more bits. So let's say this RAM 16K. It has 14 bits address. So and I'm providing over here 1 to 14. So this are 14 bits. Then why is it giving me an error? Width of internal pin buses is deduced automatically. Well, what if I do something like this? 0 to, let's say we have 13, and for this 0 to 12. Let me try to load it again. It's still giving me the error. Okay, so that means we have to provide individual bits. Is that it? Why can't I directly provide this range? Oh, wait, I get it. There are only 2 dots, not 3. So I think this might work now. Okay, it is saying that it is giving us different error now. True has no source pin. This giving us error for this thing, I guess. Okay, this should be lowercase true. Now let's try to reload it. Awesome. It is not giving us any error this time. So I'm going to load the test script directly and see if it is giving us any error or not. So far so good. That means our implementation is correct. I hope so. Or not. We have a failure at line 22. What is inside line 22? This thing is not being evaluated correctly. Set address what? What is this address? 1. Let me try to manually test it. So let's say I provide 3 as the input. Load bit 1. Clear the. Why is it not clearing it? Okay, it doesn't matter. And I want to select the first. Evaluate that. What happened? We are not getting 3 as the output, and even this RAM address didn't change. So what's the bug? Inside RL we have 1, RL1 is 0, SL is 0, and KL is 0. Okay, in this case RL1 should also be 1, right? So let's see. We have RL2 1, so this is correct. Now but this ROs are all zeros, but we should be having 3 inside. Let's see, RO should be 3. So where's the bug? We are taking the input, providing it to the RAM chip, loading the RL bit. So RL2 is 1. That means it should load this input to that particular address, and it should provide the output to RO. It is not even providing the output. That means, and it is not also storing it inside this address. So this might be where the bug is. Are we even getting 3 inside? Let me reset the whole chip and clear all of it. Or maybe I should reload it again. Awesome. Now let me try to load 5 inside the input. This will be 1. I need it inside. Let's keep it as 0. No, wait. Let's keep it 1 and evaluate. We are not getting 5 inside any of the RAM registers. and we are not even getting it inside this value. But I think we do have. So it seems that our implementation of this address mapping is not correct. Is it because it is flipped or something? Let's see if I try to load this value 16384 inside address. Let's see what happens. 16384. If I evaluate it, the screen load is 1 now, which is correct. And now if I change it back to 83, then RL2 should be 1, which is correct. Now if I pass 24575, again SL should be 1. If I pass 576, KL is 1. Can I provide 577? In that case, we have KL as 1. Is that what is causing the problem? This is the script. So it passed this test. It was giving us error for this particular address, I guess. Wait, what if we don't have this load bit 1? What if it is 0? If it is 0, then we will have zero inside all of this, right? Let me try to check it. So that's pass 0, 1, getting the evaluate option. You have to reload it. Okay. I'm still not getting the eval option. What if I provide L1? Okay, now yeah, I'm getting it. Let's get this load bit 0. In that case, all of these bits are 0, which is correct. So that means none of this input won't be loaded inside any of these chips. But we need to get this input but even though this load bit is 0, we should be getting this output. No. Light cut. Let's say we will worry about this load bit being 0 First we have to see why it is not even loading the values. So this load bit is 1. When it is 1, it shouldn't load this input to this particular address. Now that means it is not selecting the correct address. This address runs from 0 1 to 14. Check this slide again. This buses are indexed right to left. 0 is the rightmost and 15 is the leftmost. So I'm providing 1 to 14 to RAM. 1 to 14. So I'm neglecting the 0th bit, which is the rightmost bit, and I'm providing this. So we have this kind of this is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15 bits. I'm neglecting this bit and I'm providing this as the input. Wait, I think I might have a problem. These are 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. These are 15 bits, right? And for 0, all of the 6. Wait, what is it now? What if I press 1? It should select the 0th bit. If I am passing 2 over here, let me check the binary representation. This is what we are passing to the address. Now in this case, if I pass load bit 1 and let's see input, this should be 3 in decimal. I might have to reload it again. So if I pass, let's say we pass 2 as decimal value to input and 1 load bit and all of this 0. Okay, pass 1 over here. We are not getting the output in this inside this any of this. We should be getting it inside RO. Should get this value, this binary value inside this RO. If we check the decimal, we should get 2 inside this RO, but we are not getting it. That means we are not getting it inside this memory register as well. Have I used an incorrect RAM chip? I don't think so. Well, I'm passing the load bit correctly. Wait. Okay. I should. Oh, damn. I have to clock it. This RAM is a clocked chip, so we have to. We can't just click on evaluate and expect the value. We have to clock it. We have to provide one clock cycle. So after providing one clock cycle, we are getting this input value inside RO and RO2. Okay, we are getting inside RO1 and RO2 both, right? And we are getting the output inside this output as well, and we have the value inside 2. If I clock it again and again, nothing will happen. But if I pass 0, then again nothing will happen. We will have this 0 bit. Now if I change this address to, let's say, 1 to 2, and if I pass 3 inside here, then in this case we will have 0 as the output, but nothing will happen inside this RAM, right? We are getting 0. Now suppose if I provide 1 over here, in that case we will have 3 inside this RAM and 3 as output as well. Now let's try to give 16384 as the address. 16384, and let's skip load bit 0 for now. So 16384 is okay. We are just fetching this address which is for the screen and providing it as the output. Now if I pass 1 and pass 3, then we are getting this dot. I don't know if you can see it, but there's a single dot. Let me provide a higher value over here, like 340 or something. So we are getting these dots. I hope you can see it. Let me provide another higher value, like this is an illegal value. Can I provide this? Well, it's just 16 bits, so okay. So we are getting it inside the output. So this is correct, and if I provide 0 over here, the output remains same. So we are getting correct input and output for this range. What if I pass let me first pass 16383, and in this case I should get 0 as the output, which I am getting. But if I pass 1 over here and clock it, I have 1 2 3 inside 8191. Is this correct? We should be having this 1 2 3 inside 16383. So it seems we have an implementation bug in the address. We're getting the value inside an incorrect address. Getting it inside 8191. What's the problem? We are passing correct load bit, which is RL2, which will select the RAM, but the address we are passing 16383. This 16383 is mapping to 8191. Why? This is the address. 15-bit. Why is this happening? It is selecting 8191. Now 8191. 8191 is this binary value. 16-bit. We have 15-bit. Eight one nine is 0016. So these are 16 bits and 3 bits. That means 13 bits are 1. 13 bits are 1. These are 15 bits. Okay, wait. These are 15 bits, and out of 15 bits, 14 bits are 1. but apparently we are passing just 13 bits. Now, why is that happening? Am I providing incorrect range? If that is the case, let me try to check what am I passing as the addresses. For that, let me use a test gate of 16-bit and I will provide address bits 1 2 I will have to provide 1 2 14. This will be 15 bits. For 1 to 14. Okay, and B will be true. Let's get the test output inside ADD T. Yeah, whatever. Now let's see what we are getting inside ADDT. We have this variable. Now if I provide binary decimal, so if I provide 16, what was the value? 16384. So if I provide 16384, I'm getting 16384, which is correct inside this address bits. But apparently we are selecting 8192 for RAM. Now why is that happening? Selecting the incorrect register inside the RAM. 8192. Okay, yeah, right. 16884 is the screen chip. Oh, wait, and if I provide 1683, it is selecting 8191. But in this case, it should. Oh wait, so in 16383 we are getting 16382 inside the address. So that might be the problem. Or is it? Let's see what is happening. I'm providing 16383 to the address, and inside this ADDT I'm getting 16382. What does this mean? That means the last bit is being cut off, right? So if I check the binary representation, and if I provide this to this, then this last bit remains 0. Okay, I think I know what might be happening. As this address T is of 16 bits, then this address bit 0 and address bit 15 will remain 0 by default. So I wonder if that is also happening. That's the case with Okay, so for that this should be 2 to 40 15. Now let's see what it is giving. Now this time if I provide 16 383, I'm getting 32764. Okay, now that's the problem. The binary representation is okay, it has shifted now this side. Okay, wait. What if I provide 0 over here and 0 to 30? Sixteen three 16383. It is giving 8191 now. So we are selecting one less input. So we should give 0 to 15 over here. This should be 0 to 14, I guess. 14 is the last bit. This will be correct. I hope so. It is not. Well, let's see. Address and if and is of 16 bits, right? It is of 16 bits, and address is of 15 bits. So I have to get rid of one bit. This one bit is the rightmost bit. 0 to 15. This should be 14. I'm getting a bit confused. What is happening? Okay, now if I provide 16383 16, okay, I'm getting correct address now, 16383, but I'm getting incorrect in address inside RAM 16. So that means I have to provide this RAM 16 now is of 14 bits, right? 0 to 14, 0 to 14. I'm providing 0 to 14, 0 to 14, which is correct. In this case, I'm selecting the 15 bit, which is this one. Oh, wait, let me check the binary representation. I'm neglecting this bit. This is 15th bit apparently. And in case of RAM, right, it seems I'm neglecting the incorrect bit. This should be, I guess, 0 to 13. Same for this. It should be 0 to 12. Let me try to reload it again. Decimal. Now if I pass 16383 and evaluate it successful. We are selecting the correct RAM. Now if I pass 16384 and evaluate it, it is selecting the 0th RAM, but selecting 16384, which is the screen mapping of the RAM. So now if I try to load, let me reset it. I'll try to load the test script. It should work this time, and let it run. Awesome, so this time it seems it is not giving us any error. It passed this test as well. So let me run it. Let it run. Comparison ended successfully. So this means our implementation is correct. We have got all the true results for all of this test. Okay, let's see, should I continue with this CPU? So the next step is CPU, and I'm thinking, I guess the CPU will be much more complicated. So where is it? CPU. This is the diagram of CPU, and this is what we have to implement. So from the diagram only I can see that it is much more complicated. We have to use many different chips that we built previously, like Mux, register, resistor, PC, ALU, and we also need to take care of this control bits. So I don't think we can implement it in less time. So I guess we will try to implement it in the next stream. I will keep this much only for this stream. So yeah, this is it for this stream, guys. I will see you in the next stream. Bye bye.